Professor Sathyanarayana, you can start.
Yeah. Good evening. So we will begin. So I wanted to start with this problem. This is a very standard problem. I'm sure you might have done it in your courses. So a free particle. The moment we say we have a free particle, so immediately what comes to our mind is it's Hamiltonian. So the moment we say we have a free particle, the Hamiltonian of the free particle is given by p square by 2. And what else? What other information comes to your mind?
Potential 0.
Huh?
Potential energy 0, sir.
Potential energy is 0. That is why we wrote down kinetic energy only is the Hamiltonian. Okay. What else? Do you know what is the wave function for this? What are the eigenstates of Hamiltonian? So if you solve this problem, that is h psi k of x is equal to ek psi k of x. Okay, so if you solve this eigenvalue problem, you get the following. That is psi k of x is equal to 1 over square root of 2 pi into e to the power I kx. And what is the energy? Ek is equal to h bar square k square by 2. Okay, so this much we know from the free particle problem. And we also know something more. That is psi k at a later time t is given by e to the power minus I by h plus ek e into psi k at x comma t. So this is also something that we do, because every energy eigenstate will evolve with time in this fashion. Now what is given here is a wave packet. Wave packet means, so if you look at this e power ikx and this 1 by root 2 pi, so this is basically this particular equation. But now there is not one k, but there are several k's. Now each that psi k is weighted by some kind of a weight, that is gk, and that gk is given here. Okay, so these are like weight of psi k, where psi k of x is given by this. Okay, now the first question is you find out psi of x0. Second question is find psi of xt. And then compare the probability psi of x0 mod square and psi of xt mod square to Gaussian, and thereby find out sigma 0 and sigma of t. So these are the questions. Okay, so now what do we do? To find out psi of x0, what we should do?
So substitute the expression of gk into the psi x0.
So we have to just integrate this. We have to substitute this gk here, and then we have to integrate. Okay, so that is rather straightforward. So how many of you have done this problem already? Can you please raise your hands?
So this sort of problem I have did, but not the exact problem.
Okay, anybody else? Deepika, did you do this kind of problems?
Yes, sir. Fourier transform.
Okay, so this integral you have done sometime? Pandya
No, sir.
No. Abhijit?
No, sir.
Farid?
Sir, I think in inverse Fourier transform, I have seen this, but I have not done this exactly, sir.
Okay. Devismita, did you do this?
I think yes.
Okay. So let's okay, there's Satish,
No, sir.
Shruti.
No, sir, I have seen this kind of problem, but not exactly solve this problem, sir.
Solved. Okay. So please just follow this carefully. There are only few tricks or few techniques that you have to learn. So what shall we do? We first do this problem with step by step. So the first step is to find out psi of x0. What is psi of x0? Psi of x comma 0 is equal to 1 by square root of 2 pi, and then a square divided by 2 pi to the power 1 by 4. So these are constants. And then I have minus infinity to infinity dk e to the minus a square k square by 4 into e to the power I kx. Okay, that is what we have to solve. So we have to do this integral. Now these kind of integrals are called Gaussian integrals. So first what we will do is that I will write this.
So completing the square. So
Yes. So what I will do is I will write this as e to the minus ak by 2 the whole square minus ikx. Because I have pulled out a minus sign, I have written a minus sign. Now I want to do something called completing the squares. What do we mean by completing the squares? This particular thing, that is ak by 2 the whole square minus ikx. So there is a k square term and there is a linear k term. I want to write this as ak by 2 minus, okay, I will call it as some alpha, the square. So in this also you will have one k square term, one linear k term, but plus alpha square term will be there. So I don't want that term. So I will put minus alpha square. So I want to write it in this form, but I don't know alpha now. I'll have to determine that alpha. So that is equal to ak by 2 the whole square minus ak alpha. Plus alpha square minus alpha square will cancel. So if you compare this term has to be compared with this term. And that comparison will give you what is your alpha, correct? So this is the technique of completing the squares. So your alpha is equal to
Sir.
Ix by A.
Sir.
Yeah.
Sir, can you repeat that, sir?
Which one? So
Completing the squares.
So completing the squares is, I want to write this expression as ak by 2 minus alpha square minus alpha square. When you do this, what happens? Your ak by 2 whole square minus 2 times ak by 2, 2 will cancel. So ak alpha, you get plus alpha square, and that plus alpha square will cancel with this minus alpha square, correct? So now you compare term by term. So ak by 2 whole square is there here also. But minus ikx, instead of that, minus ak alpha is there. Comparing this, I can write down alpha is equal to Ix by A. Okay. So that means, what does that mean? That means this entire expression, I can write it as 1 by root 2 pi a square by 2 pi to the power 1 by 4 into integral minus infinity to infinity dk e to the power minus, I have ak by 2 minus ix by a whole square minus ix by a the square. That is this one, minus alpha square. Now you can see this term does not contain k, so this can be taken out of integral. So I square will be minus 1, minus into minus is plus. There is already a minus sign outside. So I can remove this term and write it outside. So 1 by root 2 pi a square by 2 pi to the power 1 by 4 into e to the power minus x square by a square. Integral minus infinity to infinity e to the minus ak by 2 minus ix by a the whole square dk. So this is something which we can integrate. So what you can do is you can write down this ak by 2 minus ix by a. You call this as some psi. Then dk will be equal to 2 by a times d psi. Limits don't change. So you can write this as 1 over root 2 pi a square by 2 pi to the power 1 by 4 e to the minus x square by a square into 2 by a integral minus infinity to infinity e to the minus psi square d psi. This integral is a standard integral. This integral's value is square root of pi. Okay, so this integral is equal to square root of pi. Now you can so you can see that so this root pi will cancel with this root pi. Okay, and a square to the power 1 by 4 is basically root a, and this a square and will cancel with this, giving you a root a on the top, and this root 2 will cancel to give a root 2 on the top. So you are going to have your psi of x0 is going to be equal to square root of 2 by a into 1 by 2 pi to the power 1 by 4 into e to the minus x square by a square. So this is the answer. But let us also try to find out what is the probability, that is modulus psi of x comma 0 the whole square is equal to 2 by a into 1 by root 2 pi into e to the minus x square 2x square by a square. Okay.
So you mean probability density?
Probability density, yes.
PDF.
Yeah, probability density. Density function. Okay, now I want to write it in the following fashion. 1 by a by 2 root 2 pi into exponential of minus x square divided by 2 times a by 2 the whole square. Okay, why I am writing like this, it will be clear. So this whatever is 2x square is there, I can bring it to the denominator, then it will become by 2, and put a 2 here and put another 2 here, then it becomes 4. So I can write it like this. Now why am I writing like this is because now you compare with this Gaussian. Compare with this Gaussian. Sigma root 2 pi, mu is the value at which Gaussian is peaking. So in our case, mu is 0 and 2 sigma square. So if you compare this, a by 2 root 2 pi exponential minus x by 2 a by 2 the square. So this implies we can say that sigma at 0 is a by. Okay, so that is our result. Okay, so any questions up to this?
So first of all, like GK is the K vector representation. So that is Gaussian. So Fourier transform, inverse Fourier transform will also be Gaussian. So we
Correct.
can, without solving the problem, we can the momentum representation to position representation, we can infer that. And next question, sir, I have that for free particle you have mentioned it, that the eigenfunction is like a plane wave.
Correct.
But plane waves are not normalizable.
Yeah, but this is this 1 by root 2 pi is kind of extended normalization, which you can
From Dirac delta function.
for Dirac delta. Yes.
But sir, like these are this is unphysical, no sir. Free particle cannot exist with a definite energy in quantum mechanics.
That is correct. So it will always exist like a wave packet, but
Yes,
wave
sir.
packet always can be represented as a linear combination of these plane waves.
Yes, sir. But plane wave is unphysical. In quantum.
Correct, correct.
So sir, like so this the right hand side you have what you have written that is just like conceptual like abstraction. They are not reality, reflection of reality.
Yeah, they are mathematical solutions. So free particle may not assume any of those, it may not exist in any of those states, but you can use them to construct wave packets.
Yes, sir, yes, sir. And sir, like the Hamiltonian is like a second order operator, differential operator. So we should have like two constants, like arbitrary constants, and if so two like minus ikx term will also be there. Like because free particle is moving to the plus x direction and minus x direction is move both
Correct,
sides.
correct. So psi k of x and psi minus k of x both have the same eigenvalue.
Okay, so it's degenerate.
Correct, correct.
But one-dimensional problem. This is one-dimensional problem.
Yeah. See, one-dimensional problem has no degeneracy only for bound states.
Yes, sir. If
But this is not a bound.
Okay.
This is not a bound. No, this is just a traveling state.
Yes, sir, yes, sir. Understood.
So
But
there
like,
is
I
no-
can cite one exception. Like if we have like particle in a ring, then we can have like that's normalizable. Like that's I don't know if no, that's not normalizable, but it's like it's not like blowing up.
Yeah.
Because it's
So
bounded in the ring. But it can move the clockwise and counterclockwise.
Correct.
So but it cannot be normalizable because we are employing periodic boundary condition, and it's not like it's like a wave circular like in a circular contour. The wave is like there, so it's not decaying like plus infinity minus infinity. So it's not normalizable, but that's like one-dimensional problem. That's an exception.
Correct. See, the point is what is the degree of freedom that is important to decide what is the domain of your integration, right? So there the degree of freedom is an angular degree of freedom,
Yes, sir.
and hence it's a finite interval 0 to 2 pi or minus pi to pi, something like that.
Yes,
So
sir.
there is no divergence problem.
Yes.
Correct. So there you can normalize that wave function, and there also degeneracy exists, because the degeneracy exists because it is also like traveling wave. Okay, in the ring,
Yes,
it
sir.
is in that degree of freedom, it is also like traveling wave, and hence that one dimension should not have degeneracy is not applicable there also. But if it is a bound state, like particle in a box or harmonic oscillator like that, then it is strictly, one can prove that there is no degeneracy for one dimension.
Okay, sir. Thank you.
Yeah. Okay. Any other question? Especially those of you who are seeing this calculation for the first time. Is there any question?
Sir, you gave this probability density function for x comma 0 state, and
Huh.
in that in the exponential part, I didn't understand why we wrote e power minus 2x square over a square, sir.
So when I do square, then what will happen?
So
I
it's
have e to the minus x square by a square is there. So
okay.
when I write e to the minus x square by a square into e to the minus x square by a square, exponents will add up, right?
Okay, okay. So the power will not square up. So just 2 will add up. Okay, sir. Yeah. That's it, yeah.
It is like e to the x into e to the y is e to the x plus y.
Yes, sir. Yes, sir. Yeah, I got it, sir. Thank you.
Okay. Okay. Any other? Okay. So let me assume that this is clear. And now what is our next step? Our next step is to find out. So look at this one. So we have found psi of x0, and we have found psi of x0 mod square, and then we have found sigma of 0. Okay, so these three we have done. So now we have to look at the time dependence. Now for time dependence, I want you to note that each one of this energy eigenstate will vary like this, and where Ek is given by h bar square k square by 2. So now what we have to do is so basically the idea is something like this. We have discussed this earlier, but I'm not sure if who are attending now who are also the people who were there at the time. So let me say this again. So time dependence, we say that psi of x comma t can be written as e power minus I by h cross t into Hamiltonian operating on psi of x comma 0. So this is the scheme where h is a Hamiltonian operator. This is actually called formal solution of the Schrodinger equation. Now h is p square by 2m, and p is a differential operator in x. P is h bar by a d by dx, right? So if I want to write this as e to the minus I by h cross t h acting on, let us say, integral minus infinity to infinity dk some gk into e to the power I kx by root 2 pi. So when I have something like this, this operator will not act on g of k, because this is a differential operator in x. So this will act only on this. And what is the action of this one on that? That is what we have written here. So that is equal to integral minus infinity to infinity dk gk into, you have e to the minus I by h cross into ek. Ek is what? H bar square k square by 2m. H bar square k square by 2m into t into e to the ikx by root 2. So now what we have to do, exactly like in the previous case, we have to now integrate with this additional time dependent term. That's all. So okay, let us do that. So our psi of xt now, psi of x comma t is equal to 1 over square root of 2 pi a square divided by 2 pi to the power 1 by 4 into integral minus infinity to plus infinity dk e to the power minus k square. So let me pull out a k square into, I have a square by 4 from the gk, and here I have plus IH cross T by 2m. Okay, and minus IKX. So this is what is my equation. So now what I will do is I will call it, let us define some a square of t as a square by 4 plus IH cross T divided by 2. It's a complex number, and I'm going to call this as a square of t. So what is the advantage of doing this? Then this equation will be equal to 1 over root 2 pi a square by 2 pi to the power 1 by 4 integral minus infinity to infinity dk e to the minus k into a of t, the square, minus I. Okay, so again we can do the same thing. We have to complete the squares. So completing the squares, what do we do? Completing the squares. So can someone suggest, if you have followed our previous?
Sir, minus alpha, like putting into the.
So I might, so completing the squares. So I write Ka minus alpha, the square, minus alpha square, correct? What is this
Yes.
equal to? This equal to Ka the square minus Ikx. This I want it to be like this. That means this is equal to, so Ka minus Ik is equal to this. That means this is Ka the whole square minus 2Ka alpha plus alpha square minus alpha square goes away. Now you compare this term with this term. Then you will get alpha is equal to Ix divided by 2a. Correct. But remember, always a is a function of time. Okay. So
Yes, sir.
is that clear?
Yes, sir. Yes, sir. Clear, sir.
So now what we can do, so that means this integral, that is your psi of x comma t, now be written as one by okay, can you hear me?
Yes, sir.
Yes, sir.
Yeah, I have some problem with the response time of my PC. So I think
Like it is lagging right now, sir. Little bit.
Yes, so there's some noise is
sorry, I
there.
could,
So, like, some noise is there.
yeah. So I am getting a message that that the internet resource is poor. Something. Okay, this is like writing in slow motion. Ix by 2a square minus ix by 2a square. Okay, so like in the previous case, this becomes this is independent of k, and hence this can be taken out of integral. So then we will have 1 by root 2 pi and this one a square by 2 pi by 4 into e to the power minus x square by 4a square. Always remember this is for the time. Into we have an integral, so this integral can be solved, and like in the previous case, we will get this integral as root pi divided by a of. Okay, so that is the solution. Now you can see this root pi can cancel with this root pi, and so now let's look at okay, so what is the next step? Next step is to look at this one, that is, let's look at psi of x t the whole square, the mod square, the probability density function. So that is equal to okay, the pi is gone, so this is root a, so I get a by 2 into 1 by root 2 pi, and 1 by a of t mod square into e to the minus x square by 4 into 1 by a square of t plus 1 by a square of t, the star, the complex conjugate of that. Okay, so 1 by a square plus 1 by a square star will be 2 times real part of a square divided by modulus a square whole square, right? So that is how it will be. Now remember what is our a square? A square is given by this, right? So this is same as a by 2 root 2 pi into 1 by a of t the square modulus square of a of t into e to the minus x square by 4 into 2 times real part of a square of t divided by modulus of a square of t the square. Okay, so that is what this is. Now you can, from here, you can find out from here 2 times real part of a square of t is equal to 2 times a square by, or it is equal to a square by. So that is the numerator part here, this part. And modulus of a square of t square is equal to a to the power 4 by 16 plus h bar square t square divided by 4m square. Okay, so that is what this is. Now you can write down your modulus of psi of xt the whole square is equal to a by 2 1 by root 2 pi. And what is 1 by a of t mod square is 1 by square root of a to the power 4 by 4 plus h bar square 16 a to the power 4 by 16 h bar square t square by 4m square. Okay, and exponential of minus x square a square by 2 is there in that, already there is a 4, so 8 into a to the power 4 by 16 plus h bar square t square by 4m square. Okay, so this is fine, but I just want to write this in a form. So what I will do is I will pull out this a power 4 by 16. Okay, from here, then this becomes a square by 4. Okay, that is a by 2 whole square, right? A by 2 whole square. 1 a by 2 will cancel with this, so only 1 a by 2 will remain there. Okay, so that is equal to 1 by root 2 pi into 1 by a by 2 square root of 1 plus 4 h bar square t square by m square a to the power 4. So that is what is coming here. Then let us look at this exponential part. Here also I do the same thing. I get a square by 16, a power 4 by 16 outside. And this a square and a square will cancel. So there is a 16 here. So that means 1, 2 if I write, that will be like this. So you can verify what I will get is x square divided by a by 2 the whole square. There is a 2 here, a by 2 the whole square into 1 plus you have 4 h bar square t square by m square a to the power 4. Okay, so now what is it that we are getting here? You compare again with the Gaussian. So this part, sigma root 2 pi, right? So sigma of t is given by this. So this expression is given by sigma. So this becomes sigma square. Okay, so from here we can show that. Okay, so this comes to the next problem, but let's just write this expression. So sigma of t is equal to sigma of 0. What is sigma of 0? A by 2. Sigma of 0 into square root of 1 plus 4 h bar square t square divided by m square a to the power 4. So this is our sigma of t. And you can see that sigma of t will increase as time increases. That means if you have, this is sigma is like a spread of the Gaussian, right? So if you have a Gaussian initially, that is, imagine you have something like this. You have, let's say, a wave function, and this is x, and this is time. Let's say this is t, and this is x, and this is your wave probability density function. So at time t is equal to 0, let's say that you have a very sharply peaked function like this, a Gaussian. And at a later time, you will see that this function will have a spread like this. And at a later time, this will have a much more spread like this. So this is your sigma of 0. And this sigma, that is the width of this wave function, will increase as the time process. That means wave packet spreads or disperses as t increases. So this is the result that we are able to show mathematically also, that we are able to calculate what is the expression for the sigma, that is Gaussian's width in terms of time. Okay, so we have completed. So if you have any questions, you can ask.
So I have a question, like what is the physical significance of this spread, sir? Like, as time progresses, the standard deviation increases, like, and the like peak or decrease should decrease because like area under the curve should be 1. So,
Area under the curve is same. So this means when you are when you are starting, if the spread is very small, that means there is large number of I mean there is only few around k equal to 0. There is only a few momenta that are involved in construct. Sorry, there are large number of momenta that are involved in constructing this. But as time increases, you will see, since this spread is happening, then you have so the delta, as delta x is increasing, that is spread is basically delta x here. Sigma is basically delta x. Okay, as delta x is increasing, the delta p decreases. In the limit t tending to 0, delta x becomes kind of a uniform thing. Then you can talk about one particular momentum. So the momentum thing will decrease. You can do the same thing by comparing, like for example, you try to compare this with the Gaussian. Okay, you compare this expression with the Gaussian, then your sigma k at 0 will become what, 1 by a, right? So that when you ask a question, what is sigma k 0 and the sigma of 0, this is one is for x and one is for a, this is like delta k delta x. So that is equal to 1 by a into a by t, which is equal to half. So this is like delta k delta x, but if you want delta x delta p, p is h cross k. So delta x delta p is h cross times this. So that is h cross by t. So Gaussian wave packet corresponds to what is called the minimum uncertainty wave packet.
Yes, sir. But
So
my
that is
question,
what that's what it means. That is,
yes, sir.
as delta x increases, that means the number of plane waves involved in constructing such wave packet becomes small.
Yes, sir. When I understood that the physical significance is coming from the uncertainty principle, and the
Yeah.
the, the Gaussian wave packet is minimum uncertainty wave packet. But my question, I could explain it properly. That what about the arrow of time? Like as the time progresses, the wave function in the x position basis disperses. So
Correct.
does it have any physical meaning? Like it is like entropy. Last class I asked about entropy, right? But this is not ignorance. Like,
No.
this is the intrinsic
Correct.
ignorance.
Correct.
But but entropy should be basis independent, no sir, because
Yeah.
position basis it is like entropy is increasing, but in momentum basis like
It is
it is
decreased. It's not.
converging.
Yeah. It's not related to entropy. See, this is just an uncertainty, and uncertainty in these two bases are anyway inversely correlated because of
Yes, sir.
uncertainty relation,
Yes, sir.
and that is what we observe here.
But why nature is like this? That in position basis it is dispersing. Why not the opposite? Like why it's not in momentum basis it's not dispersing? Like it could have been the opposite. No, sir.
So if you want an opposite thing,
Yes, sir.
see, this is because of the Hamiltonian. So if you want an opposite to happen, you have to ask what kind of Hamiltonian should I cook up, so that it disperses in the momentum, and then this thing happens in the time.
But so the free particle is like it has symmetry, no sir, because like it can go to the left side x plus x direction minus x direction. So
Correct.
it has symmetry, translational symmetry. So
Correct.
in a symmetric case, why do we have this directionality? It's an ontological question. I know that we should have the maturity
here-
not to ask troubling questions. So,
No, here also there is not. I mean, direction means what? You are saying direction in time, right?
yes, sir. Like arrow of
Yeah.
time.
So direction in time, that is it. It is dispersing only as time increases. Okay. So is a kind of consequence of the structure of the Hamiltonian. That's all. Okay. If you have a different Hamiltonian, this may not happen.
Like Hamiltonian is symmetric. Like it is like somehow like
It
some
is
commutative-
translationally invariant. That is correct. And that
some
symmetry.
commutation relation should satisfy some commutation relation.
Which commutation?
The symmetry, like if symmetry related.
Yeah. So
implies-
momentum will commute with the Hamiltonian. That is the translational symmetry.
Yes, sir. Yes. Because that is generator of translation.
Correct.
Okay, sir. Like I'm still thinking. Okay, sir.
Yeah. Others? Any other question? Deepika?
No, sir.
So is the calculation clear?
Yes, sir.
Pandya-Rajan?
No question, sir.
So calculation is clear?
Clear, sir. I understand.
Shruti?
Yes, sir. I understood the calculation, sir.
Okay. Okay, then shall we go to the next one?
Sir, I have a relatively off-topic question. Like we had like some disturbance in the between, no, sir. You know? So like that is some kind of noisy channel, like. Sir, so like I want to ask that this why like our the noise is present, because that is
Yeah.
like some error correcting thing is not going on in the receiver or transmitter. Like some environmental disturbance is creating the noisy channel to be noisy, but like some error correcting port should be there, no sir, to have the reliable communication, the faithful communication. This is an off-topic question, but like as we are having some disturbance. So this came to my mind.
Yeah, but this is a classical channel.
Yes, sir.
So we are having only a classical communication.
Yes, sir.
So,
Yes, sir.
some way of noise correction I think can be done, but
Yes, sir. We're adding redundancy. But why that didn't take place? Yes, sir. Like, I was reading about quantum error correction. So like this.
Yeah. But there's no quantum here.
Yes, I understand, sir. But like, because that is like a generalization of like we have the motivation from classical error correction, no, sir. Like we can have like some repeated coding, like redundancy. We add some extra bits. Like,
correct. So some kind of, that is why if you see some particular applications are much better than some other applications. Like that we say, no, let's say Zoom is better or Google Meet is better because of this intrinsic algorithms which they are using to solve some of these problems.
Let's say algorithm. This last question. Algorithm is like to reduce the time complexity or space complexity. No, sir. Like,
no, it is to do best with the least of the resources. For example, let's say that I have a very unstable internet connection. Now, with this unstable internet connection, with very low whatever kind of a data that I have, how best can transmission be done? I think that is what is
the cost of communication should be minimized. No, sir.
correct.
Like we have to like reduce the number of bits. Like we have super dense coding. We are instead of 2 classical bits, we are sending 1 qubit.
Correct.
Okay, sir. Thank you, sir.
Okay, so let us look at this problem. This is not as involved as previous problem. So given particles in the state is given by this. Alpha is equal to 1 by root 83 minus 3 times 1, 2, 3, where 1, 2, 3 form an orthogonal basis. This is in the documentation. What are the possible experimental results for the measurement of y in this basis, and with what probability do they occur? So, I mean, we have done something similar last time, but if you remember, I think last time Deepika was there and Sanjay Rajan was there, I think. And so, Deepika, do you want to say what are the possible experimental results for this operator Y? So this question, what are the possible experimental results for the measurement of Y? Deepika?
Sir?
Can you answer this question? What are the possible experimental results for the measurement of Y?
Sir, is the 1, 2, 3 a computational basis, sir? This is a different question. Right?
It's not. See, we don't know. They haven't said anything. There's some basis. Okay, computational basis is only a name, right? So
Like it's a Z. Like
So
sigma
it
z.
is it is an orthonormal basis. That means you have this 1, 2 is equal to 0, all those things, and 1, 1 is equal to 1. So these things are valid for every, if they are different, that means ij is equal to delta I.
But so y is like if we have the y like operator, then it's like eigenvectors are orthonormal basis. So that those are computational basis because it's diagonal.
Yeah. So what I'm saying is that you can take any basis. Computational basis is just a name. There is nothing like it is advantageous or something.
Like sigma z, like
That's convention. That's all. That's just a convention.
okay.
Okay,
Sir,
Farid.
is that an,
Yeah, yes, Abhijit. Go
sir,
ahead.
is that an eigenvalue we are finding out, sir? Like,
Very good. So experimentally possible results are only eigenvalues of y. So what are eigenvalues of y?
we can solve it using characters equation. In the previous class we did, like, so should
Yeah,
we do like that?
but stare at the matrix. Do you require to solve?
Yes, sir. We don't require to solve. We already got the eigenvalues. Yeah.
So it's a diagonal matrix, right?
Yeah. Yes, sir.
So what are the experimental results?
2, 3, C minus
2,
6.
3, and minus 6. Okay. So it is, I mean, you should not do unnecessary work. So if you look at it, you see it is a diagonal matrix. So they are so, they don't want you to do much work. So given problem
Yes,
is like that.
I didn't even see that. It was in front of us.
Yeah. So now this part is done. Now each one of them is occurring with what probability? The state is given by this alpha. Okay. Now each one of them occurs with what probability? That is the next question. So how do we answer that question? Farid? For example, experimental result 2 will occur with what probability?
Nine by 83.
Okay, how do we do it?
So the eigenvectors are also like obvious from the matrix.
Okay. So let us ask Abhijit. Abhijit, what are the eigenvectors?
Sir,
So let's say lambda 1 is equal to 2. What is the corresponding eigenvector V1?
sir, I think it's
So we can
2,
take
0,
a matrix, sir, and then we can solve the equation.
Yeah. So again, do you need to solve? Stare at the matrix.
2,
Isn't
0,
it
0.
obvious? Huh?
2, 0, 0.
I should get 2 out. No.
So 1, 1, 0.
Why 1, 1?
Like
Just 1, 0, 0. So if you suppose you put y on operate y on V1, what will you get? Okay, so let us call this as Dirac get V1. You will get what will you get when you operate y on V1? So y on V1. Operate it and see what will you get.
So 2.
2, 0, 0.
Yes, sir.
You will get a vector, right?
Yes, sir.
So that is basically 2 times V1, right? So this is the eigenvalue, right? This is the eigenvalue, this is the eigenvector, correct? Yes or no?
Yes, sir.
Now tell me what is the eigenvector corresponding to lambda 2 is equal to 3. What is V2?
Sir, is it 0, 1, 0, sir?
Yes, that is 0, 1, 0. So these things, once you have a diagonal matrix, these are always your eigenvectors. 0, 0. Correct. So these are 3 eigenvectors. Okay. Now I have found these vectors. Okay. Now, what is this 1, 2, 3 given? Any idea? Are these 1, 2, 3 same as V1, V2, V3?
Yes, sir, it should be, sir, because when we operate, we should get the eigen values, eigen vectors.
Correct.
So it should be same, sir, I guess.
What gives you that idea that they should be same?
Just really written this basis.
Yeah. So whenever you try to write, so it is said that y is written in this basis. This basis means this 1, 2, 3 basis. Okay. Now, when you write something in a basis, and if it turns out to be diagonal, that means that basis is an eigenbasis, right? That basis, all these vectors are eigenvectors of that. Only then you will get diagonal elements. So from here, what we found is, we found this one vector is 1, 0, 0. Or you can say that, forget about 1, 0, 0. Your y acting on 1 is equal to 2 times 1. Y acting on 2 is equal to 3 times 2. And y acting on 3 is equal to minus 6 times 3. So this 1, 2, 3 are eigenvectors. Now is it easy to solve this one? What are the probabilities? So, so look at these coefficients. This is the state. So what is the probability to get 2? This you will get by taking 1 alpha mod square, right? Because 1 is the eigenstate corresponding to eigenvalue 2. So I have to take this. That means this is the coefficient of 1. That means minus 3. That is 9 by 80. That is the probability. Okay. So you can now say that probability of getting 2 is 9 by 83. Probability of getting 3 is 25 by 83. And probability of getting minus 6 is 49 by 83. Okay. Now you can see, of course, you add them up, you should get 1. And that is 1. So these are the probabilities. Okay, is it clear? Any questions?
So I have a great question. Like, we know that the operators are like Hermitian matrices, no? So,
Correct.
so like they're eigenvalues should be real, but it's not that it's not positive operator. So in positive operator, we have non-negative eigenvalues. But we're getting like one eigenvalue -6. So that's an experimental outcome. But there are very few things in reality which the experimental outcome, they like we can have negative charge, but what are we possibly measuring that is giving us negative results?
See, negative values can come. Like for example, even if you take spin, when you calculate SZ, you get minus h cross by 2 and plus h cross by 2, right?
Yes, sir, yes, sir.
So it is basically with respect to some reference, you have a angular momentum plus h cross by 2 and minus h cross by 2, or m times h cross for LZ, m can go from minus L to plus L, right? So
Yes,
such
sir, yes,
negative
sir.
values are possible for for these things.
Okay, sir.
Sir, sorry, sir. My whole H block went blackout, so it logged me out and my internet went off for a few minutes.
Yeah. These things cannot be avoided.
So that too, I was in the question answer session correctly.
Yeah.
Sorry,
So
sir.
anybody can go out. Sometimes I was doing a slow action, right? No, it's
Sorry, sir. Yeah,
So
okay.
that
No,
noisy channel question, sir.
yeah. Okay. So if it is fine, then let's just go to the next question. So here we have an operator for a two-state system that is given by this. Okay, and if you, so this is a notation which is, if you are not familiar, let us discuss that notation. Find the eigenvalues and the corresponding eigenvectors in the basis 1. Okay. So when we say that we have a state 1, okay, and then you can talk about another state 2. What do we call this? We call this as inner product, right?
Yes, sir.
So what is inner product? You have two vectors, then you get, this is a scalar, a complex number. You will get a complex number. A complex number. Whereas this one is like a column vector. And this is like a row vector. Row vector plus complex conjugate. Okay, so this is what we know about the Dirac notation. Now we are going to talk about something like this, that is 1 and 2. Now what is this one? This is called an outer product. Okay. Now for example, if you say this one is a column vector, this is a row vector, that means suppose if you have something like A, B here, and then this is some C star and D star. Okay, 2 is like this. Then how this one, so this is like a 2 by 1 and this is like 1 by 2. So the resultant will be a 2 by 2 matrix. So this is resultant thing will be an operator. Now how do we write this operator? What do we do is we take A multiply with C star, A multiply with T star, and B multiply with C star, and B multiply with D star. So we write this as an operator. So this is a matrix, or in general we call this an operator. Okay. So now if you, so given a matrix or given an operator, Suppose, let us say that we have an operator A. So A is an operator. Okay. And let's say we have a basis. 1, 2 is a basis. Now, in this basis, this operator can be recognized as a matrix. Okay. So what are the matrix elements? It is a 2 by 2 matrix because this is a two basis elements are there. So we get 2 by 2 matrix. Now, how do we get this? We get Aij as I A J. This is called matrix element. Okay, or in other words, this 2 by 2 matrix can be written as 1A1, 1A2, 2A1, and 2A2. Okay, this is how we can write down these matrix elements. Now you look at the given operator. So given operator is given by A times 1, 1 minus 2, 2 plus 1, 2 plus 2, 1. Okay. So we want to write this as a matrix. How do we write it? So the Hamiltonian is given by A times 1, 1 minus 2, 2 plus 1, 2 plus 2, 1. Okay. So suppose I want H11. H11 is nothing but 1 H1. So when I put that, this I put 1 on either side. This term there is 1, 2. This is also having 2. This is also having 2. Only from here I will get a contribution, and that is simply A. Correct? So you want to ask what is H12? H12 is 1 H2. Okay. So this will not contribute. This will not contribute 1, 2. Only this will contribute. So that is also equal to A. Now H21, that is equal to 2H1. So this will not contribute, this will not contribute, only this will contribute. And that is also equal to A. And H22, this is 2H2. So only this will contribute, that is equal to minus A. So the Hamiltonian matrix, that is also given, but I'm just showing you how you get it. A minus A. Okay, so that is the Hamiltonian matrix. Okay. Now you can ask a question, what are the eigenvalues and eigenvectors of this? Okay. So how do you find the eigenvalues? You look at A minus lambda A minus A minus lambda is equal to 0. So that implies this is lambda square. So A square minus lambda square minus A square minus A square is equal to 0, or lambda is equal to plus minus root 2 times A. Okay, so these are eigenvalues. So lambda 1 is equal to A root 2. Lambda 2 is equal to minus A root 2. Okay, is that clear so far? Yeah, any question?
So I was thinking
Yes.
of like by inspection, can we write the eigenvalues? So like if we know the Hadamard operator, like if we have knowledge, then if we pull out A, then that will
Yeah.
be 1, 1, 1 minus 1. So
Correct.
A is like 1 by root 2 for Hadamard operator. So for Hadamard operator, we are getting plus minus 1, no, sir?
Yeah,
So
that's
here
right.
plus
If you
minus
know
2.
Hadamard, operator, you can think like that. You can do it by inspection.
Yes.
Yeah. Abhijit, you have something to ask?
No, sir, no, sir. That was clear. I said that.
Okay.
So eigenvectors we can also like by inspection we can say.
Yeah. So now let's say that you want to find eigenvectors. So can someone try and tell me what the eigenvectors are?
So is it A gate 1 plus gate 2 and A gate 1 minus gate 2?
How do we get?
So by inspection. Sir.
No, I think it's not true. Okay, so let us try that. So that is, I have A minus A root 2 and A minus A minus A root 2 into some xy is equal to 0, 0. Okay, that is the eigenvalue equation, right? So that means I have A minus A times 1 minus root 2 times x plus A times y is equal to 0. Okay, so then that is one equation. The other equation also will give you something similar, but of course we have to show it. So what we have is y is equal to root 2 minus 1 into x. Okay, root 2 minus 1 into x. What is the next equation? Next equation is ax minus a times 1 plus root 2 into y is equal to 0. Or you will get y is equal to 1 by 1 plus root 2 into x. Okay, root 2 plus 1. So this you can write it as root 2 minus 1 divided by root 2 minus 1 into root 2 plus 1 into x, which is same as this. Okay, so there is no new information you are getting from that second relation. So your x and y can be now written as x and y as root 2 minus 1 into x. Okay, so one can normalize this. So if you normalize, what happens? You get norm is equal to x square times 1 plus root 2 minus 1 the whole square. Of course, square root of this. So that is equal to square root of x times 1 plus 2 plus 1 minus 2 root. So that is 4 minus 2 root. So x times square root of 4 minus 2 root. So one of the eigenvector is the following: 1 by square root of 4 minus 2 root 2 into 1 and root 2 minus 1. This is the eigenvector V1 corresponding to lambda 1 is equal to A root. Okay. I will leave it as an exercise for you to find out find eigenvector V2 for lambda 2 is equal to minus A root. Okay, so that probably is root 2 plus 1 here. Okay, so now what this means is that this V1, so if V1, that is V1 expressed in terms of 1, 2 is like this. Your V1 is equal to 1 by square root of 4 minus 2 root 2 times 1 plus root 2 minus 1 divided by square root of 4 minus 2 root 2 times 2. So these components of this vector will become coefficients of 1 and 2. Okay, so this is how you can write it as a linear combination. So find out V2 and also try to write V2 in terms of 1 and 2.
Yes, sir, I got confused actually. Trying to
So you got confused for sigma x.
Yes, sir. Yes, sir. Like the Hadamard operator actually rotates from sigma z to sigma x. No, sir.
Correct.
So I have that information. So, but sir, like another question, sir. Hadamard of like each operator or something that the matrix you are giving is that is unitary and that is also Hermitian.
Correct. All Pauli matrices are like that. They are both unitary as well as Hermitian.
Yes, sir, but my question is like, so are they like measurement operator or are they gates?
No, when you see for a gate, it should be a unitary operator. And
Yes.
if you have something which is both Hermitian and unitary, it can be used as a gate also. It can be used as a Hamiltonian also.
How to determine what parameter influences determines whether it's a like gate or it's like a measurement tool, an instrument to measure.
No, measurement is different. See, Hamiltonian is not a kind of measurement. No, measurement means what? You have to define measurement as either a projective measurement or a POVM kind of a measurement. For that, you have to define a set of positive valued operators, right?
Yes, yes.
So measurement is altogether a different.
But so like I was like wondering like, but we said that eigenvalues are the measurement like outcomes.
The measurement outcomes, yes, because see see in a typical measurement you define projection operators by using eigenstates of that operator.
Yes, yes. Outer productions.
Yeah.
Okay. But like Hamiltonian is also like spitting out energy, no? So energy, if you measure the energy.
That's what. So if you are measuring energy, you have to have a Hermitian operator to represent Hamiltonian. Its eigenvalues are real, its eigenvectors are orthogonal, and then you can construct projection operators from the eigenvectors of Hamiltonian and describe the measurement of energy. Correct? Then
Yes.
the measurement results are eigenvalues and measurement post-measurement states are eigenstates. Whatever eigenvalue you get, that eigenstate as the reduced state.
Reduced state means I will get.
That's what. After measurement, the state changes, right? That will be the corresponding eigenstate, whichever
Yes,
eigenvalue
yes.
you obtained as a measurement.
Yes. That's the last question. Sir. Is it possible to measure like a quantity, like a state, without disturbing it? Like weak measurement, something. I don't disturb it like very little, and like it doesn't like collapse, but I gain information from that.
Yeah, so the idea of weak measurement is only to do that. That means you don't see one of the thing that weak measurements people are interested in is to get the information about the state without actually changing the state. So that is the idea of weak measurement.
Yes, sir. But that doesn't that violate the postulates of quantum mechanics?
No, it doesn't violate any postulates, because what you are trying to say is that see, the point is something like this: the collapse of the state is one way to look at the projective measure, right? The von Neumann's projective measurement theory clearly tells you that if you do this, then you are going to get the state reduction. But now the formalism is not changed. Actually, within the quantum mechanics postulates, only weak measurement also is operating. Okay. Only thing is there you will get a different that is okay. That's a little detailed discussion. So let's not worry about that now. But actually, weak
measurement.
yeah, weak measurement you can read and then look at how that is implemented theoretically.
I was reading John Driscoll's notes and I'm getting a lot of unfamiliar stuff.
Okay, so I will stop here. So my request is that you people should redo these problems on your own once, and then try and take any textbook and then try to solve some similar problems so that you can get some